So good morning, good afternoon, good evening, depends on where you are in the world. So thank you very much for joining us for a great talk today by Professor Kaushik Roy. But before I will do some brief announcements. So one of the next talks will be with Elisabetta Moisello from University of Pavia in Italy, talking about integrated interface chip for MEMS contact glass temperature sensors. Soon we are going to announce the other talks. If you lost the talks that are being done since 2020, uh, you can see all these talks in this YouTube channel. So we have more than 150 talks available. Uh, and next, LASCAS, the flagship conference of CASS, will be in Bento Gonçalves, the most traditional wine region close to Porto Alegre, next last week of February. So the deadline for submission papers is September 6th, so you have about 1 month to do that. And as you should know, there is a selection of best papers that will be published in IEEE Transaction Sequencing System 2 that will appear in the months of the conference. And during the conference, there is uh, an extra evaluation of the presentations. Then some papers will be invited for the special issue of LASCAS in CASS 1. And in 2026, LASCA will be in Arequipa, in Peru, and 2027 in Panama City. And next April 2025, we are going to have the first IEEE Latin conference on Internet of Things. So this is a flagship conference of the IEEE IoT technical community that is sponsored by 12 IEEE societies. Then, as you should know, each year we have SBCCI in Brazil that is also sponsored by IEEE Sequencing System Society. So this year it will be in reality beginning of September. There was a change of 1 week, in João Pessoa, in the northeast of Brazil. But next year it will be back to Manaus after 25 years for a next edition of the Chip in the Jungle. So we will still have plenty of time to prepare your papers to submit for this special edition of SVCCI. And as you know, CASS is celebrating 75 years this year, and there is a promotion that if you were not a member yet of CASS, you have a free membership, and this free membership is available till the end of this month, because from September it starts the membership for 2025. So, but we are here today to attend the talk by Professor Kaushik Roy from Purdue University, USA, Rethinking Computing with Neuro-inspired Learning, a system technology co-design approach. So Professor Kaushik Roy is the Edward Tiedemann Jr. Distinguished Professor of Electrical and Computer Engineering at Purdue University. He received his bachelor from India Institute of Technology in Kharagpur, PhD from University of Illinois at Urbana-Champaign in 90, and joined the Semiconductor Process and Design Center of Texas Instruments, Dallas, where he worked for 3 years. Kaushik has supervised more than 100 PhD dissertations and is the co-author of 2 books on low-power CMOS VLSI design by John William McGraw-Hill. Kaushik received the National Science Foundation Career Development Award in 95, IBM Faculty Partnership Award, ATT Award 2005, SRC Technical Excellence Award, SRC Inventors Award, Purdue College of Engineering Research Excellence Award, Outstanding Mentor Award, Humboldt Research Award in 2010, 2010 IEEE Sequence System Society Technical Achievement Award, Charles Karagapur Fulbright Nehru Distinguished Chair, DOD Vannevar Bush Faculty Fellow, 2014 to 2019, SRC Aristotle Award in 2015, Purdue Arden Biment Junior Award in 2020, SRC Innovation Award in 2022, honorary doctorate from Aarhus University 2023. So full of awards. No? Congratulations, Kaushik. So now the floor is with you to start your talk.
All right, thanks, Ricardo. Can you see my screen?
Yes.
Okay,
It's okay.
great. All right, thanks for the invite. So what I'd like to do today is talk about neuro-inspired learning. We all know that deep learning certainly has made a huge amount of progress. However, despite this tremendous progress in AI, the biological systems still possess a level of functionality that is unmatched in artificial systems. And this is an example of that. One of the examples that you can see at the bottom is the fruit fly. It turns out that fruit fly can do various interesting maneuvers and can potentially do fly very efficiently and effectively with about 100,000 neurons. Turns out that the power consumption, and if you only consider the compute power, that's about 50 microwatts in a fruit fly. On the other side of it, as a part of an IAPA project that we had, our project was to sort of fly like a fly. Obviously, we couldn't do the maneuvers that the fruit fly does. So, but we developed actually, as a part of that work, a UAV called the Flying Monkey, developed a DuPen, and turns out that the compute power of that was about 1 to 2 watts. So there's a huge difference between that microwatts versus the 1 to 2 watts. And as we go above the chain and look at the humans versus the AI machines today, the AI machines do end up taking huge amount of power consumption of the order of 10 to the 6 watts or so for the AlphaGo, whereas on the other side of it, the human possibly about 20 watts of power. So there's a huge efficiency gap between AI and natural intelligence. So we in our lab also did some work, and we actually wanted to see if we can implement an efficient detection system, implementing a RetinaNet DNN in a smart glass on a Google Edge TPU. And what we found is that under ideal conditions, the battery life for that smart glass would be about 1 hour or so. But if you consider, for example, the non-idealities, including, for example, display power and all, the time for the battery life is possibly going to be half an hour or so. So the question, of course, is we certainly see an existential proof that the brain is quite efficient. So where do these inefficiencies come from in our artificial systems? And they do come from the fact that we don't certainly know the right algorithms in our brain. The hardware architecture of the brain, where these algorithms are certainly implemented, is nothing like the von Neumann architecture. We certainly don't have a CPU on one side of our brain and the memory on the other side. They're all mixed together, and the computing is done in some very interesting ways, which we don't exactly understand. But the compute and memory sort of are intermingled in a lot of ways. And at the end of it, the circuits and devices to implement the neurons that we have are still CMOS devices, while they have been the workhorse of most of the advancement in computing technology that has been made. Turns out that they may not be very efficient in implementing synaptic operations or neuronal operations. So to that effect, the question, of course, is can we take some cues from the brain? knowing that the brain is certainly efficient. So what are the different cues that we can potentially take? First of all, how about the neuron model? Now, in general, today, for example, most of these neural networks, I mean, the standard artificial neural networks are certainly weakly inspired from the brain, and the activation functions are mostly ready. Uh, Now, on the other side of it, the biological neurons are more sort of like a leaky integrate and fire kind of operation. No, stochasticity has also been observed in neuronal firing. So, is it possible that we use for better, system design? Is it possible to use, leaky integrate and fire kind of neurons, or an integrate and fire kind of neuron, or maybe even a stochastic neuron? The learning algorithms today mostly are backpropagation, and backpropagation is a good theory behind it. And the networks can be optimized based on the backpropagation learning group to learn a particular data set and to be able to generalize it. But it turns out that backpropagation is expensive. Is it possible to do some local learning? Local learning certainly has been observed in the brain. An example of that could be spike timing dependent plasticity. So the question, of course, is, hey, is it possible to use that effectively? On the other side of it, if you were to really think about, the more bioplausible learning, the neuroscience folks have been talking about the dorsal and the ventral system, and the dorsal and the ventral system are effectively really the what and where of the things that we're looking for. So can we then, use, for example, foveation and the, saccades for learning? And I'll talk about that briefly later on. How about the network topology? In general, we are used to using, for example, for example, for image recognition, BGG nets, res nets, and all. But there isn't really a good way of determining what is a good network architecture. Should there be long-range connections? Should there be feedback connections? Should we take any cues again from the visual cortex of monkeys? There's been a good amount of work that has been done on the visual cortex. Can we take some cues and really come up with a network architecture which is more suitable for, for example, let's say for vision tasks? On the other side of it, how about the computing principles of the brain? In general, as I've talked about it earlier a little bit, that the communication and the compute, should they be tightly integrated as we see in the brain? Should we have asynchronous event-driven computation if we are computing with spikes? And finally, at the end of it, the input sensors do play a very, very important role. So the question, of course, is what kind of input coding that I should use? Should I actually use direct analog inputs from, let's say, for vision tasks, or should I actually code it into rate coding? Or should I use, for example, more bioplausible cameras like the DPS camera and so on? So those are all very, very important questions. And for a system design, as we'll see, that one has to think about, certainly the right kind of neural model, the learning algorithms, the network topology, and the computing principles. But, at the end of it, all these different, sensing, learning algorithms, and the network architecture, they have to be implemented in the right kind of hardware. And at the bottom of it, the hardware is, developed using the right kind of circuits and devices. So to that effect, we believe that in order to actually make systems efficient, there's a need to be co-designing, the the algorithms, hardware, and system architecture so that we can get an optimum design. So the sensing hardware, the sensing techniques, the network architecture, the hardware algorithms, and possibly at the end of it, the circuits and devices need to be co-designed to get efficiency. So to that effect, before I go into the co-design aspects of things, let's take an example for the system technology co-design. And to that effect, I take an example of the vision-based navigation, where let's say a drone is supposed to go from point A to point B, avoiding objects, and the objects can be moving objects, the objects can be stationary objects. So to that effect, what the drone has to then do first is to be able to figure out what's around it using the vision sensors that it has. let's say. And so that includes, for example, optical flow. How are things moving around me? I have to be able to, and the drone has to be also able to, determine what the depth of all these objects are. So that will be depth estimation. It has to do segmentation, moving objects. It has to be able to track objects, and then basically decide, hey, how do I go from point A to point B? Do path planning, and then take proper actions of how to go from point A to point B. So if I have to break it up into what kind of sensors then I need to use, one example could be that I use a standard camera for these vision tasks. But it turns out that one can also use these more recent, new, interesting cameras, which are even cameras which are quite bioplausible. And turns out for these even cameras, when there's a relative motion between the camera and the object, there is a spike that is produced. The spike can be a positive spike and a negative spike, depending on how the intensity changes. And using such spikes, one can potentially try to do computations of tracking and other things, as I'll briefly mention later on. Now, one of the interesting things about such a camera is that when there is no relative motion between the camera and the object, then there will not be any spikes. So it can potentially go into a very low power. Now, once these inputs are available, the question then becomes, hey, how do I do my optical flow, depth estimation, segmentation, object detections, and so on, as I mentioned earlier, for my perception tasks. Now, these algorithms of optical flow depth estimation, say, has to be implemented in the right kind of neural networks. And as I mentioned earlier, that the cameras can be, in this particular case, both frame-based cameras and even cameras. And it turns out the even camera outputs are quite suitable for implementation using a spike-based computation, which are a spiking neural net, and which has a leaky integrate and fire kind of activation function. Whereas on the other side of it, if you're using frame-based cameras, it's not that you can't use an SNN. Effectively, one can also use a standard DNN kind of architecture. Now, in order to effectively implement these network architectures to be implemented in the right kind of hardware, what we found is that in a lot of cases, hybrids of SNN and ANN kind of architectures are more suitable. They can give you the least amount of parameters required, and at the same time, they're able to also effectively capture, for example, the sequential information that we're talking about. Now, once you have these architectures, one has to really think about, hey, what kind of hardware architecture should be there to implement such, hybrid kind of networks. Turns out, and I'll go into a lot more details about such architectures. It turns out that, I talked earlier about the fact that it's way more effective to have the computation to be done in the memory itself. So if I'm able to do, for example, in-memory computing, could be digital or could be analog kind of in-memory computing, it turns out I can potentially get a large amount of improvement in these AI tasks that I'm talking about, especially for implementing some of these, hybrid neural kind of architecture. There are other kinds of optimizations that one can do, and one can co-design the algorithms and the hardware so that they can effectively work and get the largest amount of accuracy while at the same time achieve, lower power consumption. So let me just focus now more on the hardware fabrics part of things. And as I mentioned earlier, that these neural networks that we are talking about, and they implement, they do a lot of these. I mean, for training and for inference, what you need to do is you need to do a lot of matrix vector multiplication. So what I'm showing on the right side is chart that's borrowed from IBM, which shows for speech, language, and vision kind of processing, most of the computations that we end up doing are GEM, which is generalized matrix multiplication, which is shown in red, or matrix vector multiplication. So those are the main computations that you need to do. Now, for today's new architectures, like transformers and all, it turns out that not only these matrix vector multiplication, but also softmax computations are also very important. So if there's a good way of accelerating these matrix vector multiplication or the softmax operation in a customized architecture that can potentially give me a large amount of improvement in computation and energy consumption. So to that effect, on the right side, but I'm also showing that for softmax, you need to actually effectively be able to very quickly compute exponential functions that can also lead to fast computations of tan hyperbolic and sigmoid, and if I can do it in the memory itself. So the circuits and architecture that we then need to develop for the kind of network architecture that we talked about are the circuits and architecture that can efficiently implement these algorithms and possibly embody the computing principles of the brain. And that could be, for example, near and in-memory computing. And the reason why that is important is because then we can reduce the data movement cost. So anytime we try to do these computations as matrix vector multiplication as an example, you don't have to certainly fetch data from the memory, bring it into your computation. You need to do the computation and bring it back to the memory. It turns out that these data movement costs can be quite large in today's standard von Neumann computing systems. So the question, of course, is, hey, can I do some of this computation in the memory itself? As I mentioned on the right side, that softmax computations or tan hyperbolic or sigmoid could also be important. And in general, transcendental functions or map tables are kept in a DRAM. So is it possible that I can keep some of these computation units within my standard memory? And if I can do it at no extra cost, then I can potentially be able to do my softmax and tan hyperbolic or sigmoid computations also faster. And I'll go into that a little bit later. Turns out that most of deep learning is error resilient in nature. So to that effect, is it possible that I can do some approximations? So what are the approximations one can potentially do? Quantization. Quantization has been quite heavily used, quantizing the weights, quantizing the activation values. If I can do that effectively, then I can get potentially a large improvement in area and also at the same time computation cost. It has been also observed that stochasticity can be effectively used in neurons to build stochastic hardware that can potentially not only give you energy improvement, but at the same time can give you better generalization in some cases. If I were to then do, for example, on the other side of it, computations with spikes, it turns out event-driven computation is important. And finally, at the end of it, one has to also think about, what kind of devices should I use? Should it be the standard CMOS technology? There's been a good amount of work in the recent past that has been done on, these non-volatile memory technologies. Can some of these non-volatile memory technologies, could they represent, synaptic operations better? Can they do actually mimic neuronal operations? So those are also quite important, and we'll try to talk about some of those a little bit later on today. So where are we today? Today, we are using multi-cores and GPUs and different kinds of accelerators for these AI applications. But for the kind of hybrid, architectures that we just talked about and the need for it, one can potentially look at, in-memory computing, approximate and stochastic hardware. And if I'm able to effectively do such computations in memory and do, again, approximations that I talked about, one can potentially get a large amount of improvement. So to that effect, let's try to switch gear a little bit and really talk about what are the different devices that one potentially use, other than, of course, CMOS. Here I'm showing a good number of these colorful devices. But what is really important to, what I'm going to be focusing on is on the right side of it, the devices which are a little more mature, like, for example, the RRAMs, the PCMs, the STT-MRAMs or the SOT-based MRAMs, or in fact, even the ferroelectric, transistors or capacitors. On the left side, you see other kinds of devices like skyrmionic devices or lateral spin valves and all. Those are certainly a lot more. There's a lot more research to be done to make them into mainstream. Now, among all the devices that I talked about, turns out each has its own kind of characteristics. And if I now try to compare some of these devices, these non-volatile memory devices like STT-MRAM, RRAM, or PCM, each has its own kind of area requirement for implementation as a memory cell. So if I were to really look at the cell area for the PCM and the RRAM can potentially be quite small. MTJs would be certainly larger than that, but for the similar kind of technology, SRAMs would be slightly larger. The right energy consumption, that turns out to be quite important for, at least certainly for training. The right energy consumption of PCMs and the RRAMs are way larger than, for example, the magnetic tunnel junctions or, for example, the CMOS SRAMs. Turns out light latency, that also plays a very, very important role for PCMs and RRAMs. Those are quite large. But finally, at the end of it, what is also important to understand is the endurance of some of these devices. In particular, actually, the PCMs and the RRAMs, both read and write endurance, can be quite low, of the order of about, as I'm showing, 10 to the 7 to 10 to the 5 cycles. The magnetic tunnel junctions are certainly quite higher, 10 to the 5 or so, 10 to the 15 or so cycles, whereas the CMOS SRAMs are larger than 10 to the 16 cycles or so. So these different characteristics of these devices can potentially be now used, and the architectures can be co-designed so that you achieve the kind of energy efficiency and the accuracy that you want. So to that effect, let me just focus on, as I mentioned earlier, that I'm going to focus on computing memory and try to explain what computing memory can be. Now, CIM stands for computing memory. I also put in this other term RIM, which is basically doing a ROM in a memory, and I'll talk about that for these transcendental functions like exponential functions, sine hyperbolic functions, and so on, mainly for machine learning applications. So let's try to look at the computing memory. And the standard memory technology, what we end up doing is we usually turn on a single word line. And then there are peripherals like the sense amplifiers, which are there to be able to read the bits. It turns out it works perfectly well in a 60 cell, and one can potentially also think of the standard RRAMs and other kinds of memories which can follow such technology. Now, turns out that if I'm able to somehow turn on multiple word lines, in this particular case, 2 word lines together, and each word line is associated with some voltage V1 and V2, turns out that one can actually do some bitwise AND operations, bitwise OR operations, XOR operations, and by adding a little bit of extra circuitry, you can do addition operations. May not be able to do that directly in a standard 60 cell, but with some modifications, you'll be able to do it. But turns out that you can very effectively do that in this 2-terminal devices, like RRAMs, STT-MRAMs, and PCMs, and so on. So, but the peripheral circuitry increases a little bit. Now, if I'm able to now turn on multiple word lines together, and by adding some extra, interface circuitry, which I'm showing at the bottom, turns out you can actually do matrix vector multiplication, and that's an analog operation and the core, compute requirement in machine learning. So if I'm able to do such matrix vector operation or a matrix operation, then I can actually potentially save a lot of power consumption. But this computation that I'm showing on the right is an analog computation. So at the end of it, the peripheral circuitries required to be, they need to be converted from the analog domain to digital domain to be processed in the next stages and so on. So that can potentially be an extra cost, and also the SNR of such memories need to be considered. So can I use, for example, SRAM's non-volatile memory technologies? The answer is yes, and I'll be going to that. As I mentioned earlier too, that I talk about this RIM or having a read-only memory embedded in a RAM and at no extra cost. And it turns out it's also possible to do that. And if I'm able to do that, then I can also do some of these transcendental functions like exponential functions and all in the memory itself on my on-chip memory. The next question that comes up is, since we understand that computing memory is important, so what are the what, when, and where of CIM? So what do I really mean by what? First, let me talk about where of these, where should these in-memory computing be done? Should this in-memory computing be done in the register files? Should it be done in the shared memory? Should it be done, for example, in the main memory or in the DRAM? Where should it be done, or should it be done everywhere? The second thing that is also important is that what kind of computing memory should I use? Should it be analog primitive? Should it be digital primitive? What kind of in-memory computing should I use? The final question, and as I said, some of these are good. The digital or the analog can go into these shared memories, the register files, or the DRAMs and so on. The final question that one has to also ask in terms of CIM is, when should I do it? And so what do I really mean by when? It really depends a lot on the workloads. So what kind of workloads do I have? Is it a memory-intensive workload? Is it a compute-intensive workload? And depending on that, turns out in-memory computing can be useful or not. So with that in mind, let me just go into the fact that, hey, what are the different ways I can do these, important computation units of AI, which is matrix-matrix multiplication. So how do I do this matrix-matrix multiplication? I am talking about this analog in-memory computing to start with. And if I do have a bunch of inputs which are coming in, V0, V1, Vn, then if I do have a crossbar like this, which I'm shown here, which each of these elements, which are shown in red, which is basically are the conductances. And these conductances are really some of these interesting devices that I just talked about earlier. Could be a PCM, could be an RRAM, could even be actually STT-MRAM or a CMOS technology. And if I have this voltage right here, what I get at the output is a summation of, Kirchhoff's law, a summation of VI times GI, which is the conductance. And that's effectively, I end up getting my dot products or matrix vector multiplication. Now, this efficient MVM unit that I'm showing here, you have to be careful about such implementations. Now, interestingly enough, a few things that I didn't talk about in this MVM unit is that you need an access device. And what kind of access device? That could potentially be a transistor. And people have been looking at other kinds of two-terminal access devices, which can be smaller, but there hasn't really yet been a very effective two-terminal access device. So it's still going to be possibly a transistor kind of an access device. Now, what is also important to understand is that I get these analog computations, in this particular case, as a current to be doing this matrix vector multiplication. But in order to communicate to the next set of MVM units, it turns out it's important that I actually have these peripheral circuitries. And these peripheral circuitries can potentially be an analog to digital converter. The reason why you would like to convert it into the digital side is because in communications, if I do it in an analog domain, all my analog errors are going to get added up, and that can have a catastrophic effect in terms of my accuracy. So to that effect, one can potentially now think of, and I'll go into slightly more details of this architecture, one can potentially think of having these MVM units, which can be connected to other MVM units in an architecture which looks somewhat like this, with this network on our chip kind of architecture. I'm not showing all the details here. In the next slide, I have some more details to show, but this is the kind of architecture one can potentially think of, a spatial architecture like that. And then one can also think of having an off-chip high-density memory. Now, as we'll see later on, in such an architecture, these peripheral circuitries, these analog to digital converters that I just mentioned, they are going to be the dominant component, unfortunately, both in terms of area and in terms of energy consumption. And the larger the crossbar array, the more the complexity of the ADC that you have to do. And it turns out that can take up a good amount of area and the energy consumption of the chip. Even though such an architecture potentially can be quite better than a GPU kind of standard von Neumann architecture, however, still you're going to be dominated by the ADC units. Now, there's a little more details on this hardware architecture that we developed earlier in collaboration with HP and with the University of Illinois. This is an architecture called PUMA. And this was presented back in 2019 in ASPLOS. The basic architecture has these cores, core 0, core 1, and so on in each of those tiles. And the cores basically consist of these MVM units that I mentioned in the previous slide. They have a little bit of an extra memory in there and some a little bit of compute units right in each of those cores. Now all these cores implement this matrix vector multiplication, but remember that I might have to do these large scale 1000 cross 1000 or 2000 cross 2000 matrix vector multiplication. Turns out from the technology point of view, you may not be able to implement these large scale crossbars. I might have to break up my crossbar into smaller units and then accumulate the results. And that's why we need these different cores. And then finally, at the end of it, the tile is going to have some receive buffer and some shared memory. And I end up repeating a large number of these tiles in a network on a chip kind of architecture to get my hardware, which is a programmable accelerator for machine learning inference. And it is basically massively parallel accelerator, amenable to data level parallelism, and quite efficient for, as I mentioned, for machine learning inference. Now let's go into our in-memory computing unit into a little more details. Can I do these in-memory computing using an SRAM-based in an SRAM architecture? So to that effect, I'm basically first going to talk about a digital CIM, which is going to do bitwise vector, Boolean operation. And in this particular case, hopefully it's readable. What I'm showing here on the left top is that these are 80 memory cells. 80 memory cells are kind of interesting in the fact that the standard 60 is really used for writing, and these two extra transistors, which I'm showing here, are for in the read path and therefore read operations. See, these cells have a separate read and write port, which is good, and they can be separately optimized for read and write. So they have a read word line and a write word line. So I'm not showing here the write word lines, but it turns out that if I can turn on two of these read word lines in a particular memory, then with some extra circuitry, which I'm not going into the details of, I'm able to do bitwise and other operations. And if I add a little more circuitry to it, I might actually be able to also do addition operations and so on. So to that effect, one can also, in these 80 cell, what one can do is a single cycle read, compute, store operations. So what one can potentially do is we can turn on two read word lines, do these bitwise operations of and or in fact even a addition operation we do, and then simultaneously can turn on this write word line to be able to read in this particular location that I'm showing. So it's actually can be quite efficient. You certainly have to pay in terms of about 30% extra area for such memory compared to a standard 60 cell. So what my system for in-memory computing looks like, it is somewhat like this. I have a processor, main memory, and on-chip memory, which can and these memories can do enhanced in-memory computing operations. So a conventional instruction would be, for example, to do add operations would be load the values, then add in the CPU, and then store operation. Instead of that, one can potentially now think of one integrated operation of compute in memory add, which is operating on these two address 1 and address 2, and storing it value in address 3. And that can be potentially quite efficient. Now, this is basically a SIM memory code that we actually implemented. I would like to mention that this is an analog in-memory core, where in this particular case, we actually turned on multiple word lines. Now, a few things which are important is that if I turn on multiple of these read word lines, then I can, and if I precharge my bit lines, the read bit line high, then I am actually able to do these matrix vector operations on that bit line, and then I can have sensing circuitry, in particular actually an analog to digital converter, to be able to actually convert the matrix vector multiplication operation. So that's what I'm showing on the right side of it, that you actually have an analog mask and the read operation and ADC operations. In this particular case, we actually ended up using an ADC which is reconfigurable. Now, why is that important? It turns out that there's a good amount of sparsity available in the inputs. If 50% of my inputs are 60 or 80% of my inputs are zeros, turns out that if I'm able to detect that, I potentially don't need to use a full precision ADC. I can use I can use a much smaller precision ADC. So if I have a reconfigurable ADC, and if I can detect the sparsity, then I can potentially actually have a reconfigurable architecture, which can, depending on the sparsity, use the right kind of ADC, and you can get improvement in terms of, again, energy consumption. Need to do on-chip row and column rearrangement hardware support, also for load balancing and so on. Now, if you do that, we implemented that sort of in a 65 nanometer technology with a voltage of 1.2 volts. Now, what I really wanted to underscore here, the fact that even though that the architecture that we're using here is it can potentially have a full precision ADC, and it can give good accuracy, and the on-chip energy efficiency is about 1.4 to 6.7 tops per watt, and the CFAR 10 accuracy that we can get on this architecture is about 91.8%, which is reasonable. Turns out, if you break down the power consumption, it's again dominated by the ADC components, which are shown in red. And that is a major issue. And that also tells me that since I am area constrained in terms of the ADC size, I may not be able to put ADC in each column of that memory. So rather than that, what I'm going to probably use in a 64 cross 64 crossbar, what I'm going to do is possibly use one or two such ADCs, and then I'm going to multiplex it. And that basically slows down the operations. So the next question, of course, is that, hey, is it possible that I use co-designing algorithms and circuits to get rid of ADCs completely in such an analog computing memory? And it turns out it's indeed possible to do that. So basic idea here is that you have to do what we call co-designing of the architecture or the algorithm with the underlying architecture. So you have to train now the DNN model with partial sum quantization. I'll go into that in just a moment in the training group. So what does it really mean is that if I were to start with, if I now take this crossbar, right, which I'm showing in the bottom left corner, turns out that instead of an ADC, I can replace the ADC with an SA, which is a sense amplifier. Now, if I do that, and if I don't do anything in my trained architecture, I'll have a severe, degradation in accuracy. However, now if I train my network architecture with, for example, this quantized ADC, in this particular case, 1 bit, when the partial sum is quantized to 1 bit binary values, it turns out if I do that, and there'll be multiple of those crossbars, right, to be able to do the computation and then I accumulate the results. If I can put it in the training loop, or in other words, I not only would learn the data, but I'd also learn the architecture, the quantizations that I have in the architecture. If I do that, then I can almost get back my accuracy. So that's the kind of training that you have to do. You have to put the hardware in the loop for training, and that can potentially give you back your accuracy. One other thing that I'd like to mention is the fact that even though these sense amplifiers, I'm putting it as 1 and 0, one can also do, for example, 1.5 bit ADCs, meaning thereby that I can potentially have a sense amplifier at the output of each column, where the outputs of the sense amplifiers and sensing can be 1, 0, or -1. Now, one other thing that one has to look at is that during training, what we also get are these S or these factors that I need to do that are to multiply each column. These factors S are basically learnable parameters, and that's the thing that I have to do is I have to multiply the output of each of those columns with S associated with each column. And that's a trainable parameter. Unfortunately, that's going to cost me. However, it turns out I can also parameterize and optimize S to take, quantized values, 4-bit values, and it turns out 4-bit or 8-bit values. And if I do that, and if I do such computations in the memory itself, also digital computation, I can potentially get a large improvement and I can get rid of the ADCs completely. And this is basically the results that I'm showing you, that if I don't do any training and use this 1-bit quantization with ADC-less or 1.5 bits, which is that's 2 SEM75s that I showed, if I don't do anything, accuracy suffers a lot. But if I put that in the training loop, which is shown in black, then as you can see that we can get back our accuracy almost like the full accuracy level that we had. So that is something which is important, that you have to really do these co-designs. So far, I talked about CMOS-based non-volatile memories. It turns out you can actually also have NVM-based SIMs, and so now potentially can I really use these NVM-based SIMs and co-design algorithms, devices, and circuits for proper operations. Turns out that is quite important in terms of NVMs, and there's reason why it's going to be important is hopefully that's going to be clear in the next slide, that you have to co-design your device along with the architecture and the algorithm so that you can get the most benefit. Else, you may not even be able to utilize it. So let's look at an NVM. Remember the NVM characteristics that we looked at. One of the things important to note is the fact that at the device level, in particular, actually, if I look at STT-MRAM as an example, the magnetic device as an example, they certainly have good storage capacity, but they can store a single bit, which is not a problem. Endurance is high, but it turns out, and the write energy is low, the conductance drift is low compared to an RRAM or a PCM. But what is really problematic here is the fact that the R-on to R-off ratio for an STT device is low. So in other words, the TMR of the device is probably 100 to 200%, and that's quite low. And that also tells me that I may not be able to build large arrays because my R-on to R-off ratio is small. So the question then, of course, is the fact that, hey, it has better characteristics in a lot of ways than an RRAM and a PCM. Endurance is much better. So can I really now take this technology and make it efficient for AI applications, and in particular, actually for crossbars? So the problem, as I said, is there's a need for really thinking about device circuit co-design. Now, why that is important, as I mentioned, that for such a crossbar that I'm talking about, what is really important to understand is that the on-off ratio is small, and if the on-off ratio for a device is small, one can show that when all the devices are off, all the inputs are off, leakage can be a problem. That's one thing. The second thing that is also a problem is really sensing because of the R-on-R ratio to be small, so it's difficult to build large crossbars. And so what can we do? It turns out you can do different kinds of device optimizations, and considering the fact there's a good amount of sparsity. Remember, I talked about sparsity during SRAM in-memory computing. So if I can effectively utilize sparsity, if there's a large amount of sparsity, potentially I can increase the size of the crossbar. And the second thing that is also important to understand is that if I can do some device optimization, then I can potentially also have a larger crossbar and have less computational errors due to non-idealities. So what are the device optimizations I can do? The device resistance is important. So now if I can increase my device resistance by, and the TMR of the device can be improved by slightly increasing the crossbar and the oxide thickness. Now, if I increase the oxide thickness, the good thing is that certainly my TMR increases, my on-off ratio improves slightly, but the problem that happens is that my read is going to take more current now. So I pay for it in terms of read power consumption. Now, in an SOT device, in this particular case, we're talking about an SOT device. Since I'm not writing through the magnetic tunnel junction stack, it turns out I'm writing through the through a heavy metal. Turns out that my write doesn't get affected, and that's important. So now, if I can optimize my device, MRAM device, so that STT MRAM, I'm going to have a problem, as I said. If I make my MGO thickness slightly thicker, my write current is going to also get affected quite a lot, in fact, exponentially. But if I have an SOT device where my write goes to this heavy metal in green that I'm showing at the bottom, then one can separately optimize it, make my MGO slightly thicker. And what we can show is that now one can design larger crossbar arrays, which I otherwise couldn't have done. In this particular case, I'm showing that one can potentially, with this larger crossbar array, and effectively utilizing the sparsity and requiring fewer ADCs, one can, or the ADC complexity, one can actually have an energy improvement about 3.8 to 6.3x with minimal accuracy loss compared to the case where we do not optimize the devices. Now, co-design is also required and possible in case of RRAM-based accelerators. Remember, in RRAM, one of the problems was, or PCM problem was endurance. And due to endurance problems, it's difficult to write to the RRAMs too many times. So if I were to use, for example, an architecture which is a training architecture, requires a huge amount of writing, then of course, I'm going to have problems. I may not be able to use such a device. But the question, of course, is, hey, can I change my architecture? Can I co-design my architecture and the algorithms together to be able to use such devices even for training? And to that effect, that's what we looked at, a hybrid RRAM-SRAM partitioned architecture. And the architecture looks somewhat like this. I know that RRAMs are, certainly efficient, dense on-chip storage. That's the pros. The cons are functional errors due to non-idealities, and write power is really huge. There's huge, lower endurance, and that doesn't lend itself to trainability. On the SRAM, on the other side, the pros are the compute accuracy, trainable due to high endurance, but the cons are slow and inefficient. MVM due to high, off-chip data movement costs, because they can be potentially larger. So is it possible that I come up with an architecture which is, in this particular case, a hybrid RRAM-SRAM architecture, which I'm partitioning it such that I do, for example, transfer learning. So the SRAM part of it, what I'm showing here is an architecture where the later part of it is SRAM. The earlier part of the architecture is basically RRAM-based crossbars. But since it is basically a architecture which is using transfer learning, the first part of the devices, which is basically the RRAMs, are trained and written once. Now, in the training architecture, when I update my weights, I only update the SRAM weights. These are the trainable weights, are the SRAMs. The weights which are transferred from transfer learning are in RRAM. So basically during training, the RRAMs are only used for forward propagation, meaning thereby that I can actually look at the non-idealities and that can get included, in fact, in my training. No back propagation through it. The back propagation is done only through the SRAMs, and updates are done in the SRAMs. And that basically leads to an architecture which is a hybrid architecture, taking advantage of the fact that, hey, RRAMs are fast and efficient and small, but and dense, but doesn't have the endurance. So I can still use it in an architecture like that. So this such a hybrid architecture we implemented and showed that it's quite effective for training applications. But important to understand that transfer learning is what we can use here. A few other things I quickly wanted to talk about: transcendental functions. So far we talked about matrix vector multiplications. Is it possible to use these transcendental functions? And what one can show that I can also store, you know, exponential functions or other kinds of transcendental functions in my memory itself, but I don't want to take up extra area. So what we did is we looked at embedding a ROM. It's almost overlaying a ROM on top of a RAM. It doesn't cost extra. Effectively, you can potentially think of a ROM to be 1 MB, and at the same simultaneously, you have a RAM of size 1 MB. So the size is going to be twice the size. Half of it's going to be ROM and a RAM. It's not half the size, but you actually get the size of the ROM to be free almost. And so how do I get that? This is an example of an STT RAM, access transistors and the STT devices could be for RRAMs. One can also show with modifications can be done for SRAMs, which are non-volatile. That's a problem, but can still be used. But let's try to look at how the ROM is overlaid on the RAM at no extra cost. So this is my word line, which I'm showing in yellow. If I turn on the word line and try to do the standard RAM mode operations, then what I show here is that, I have a source line and a bit line. The bit lines are usually one bit line, but in my case, in this particular case, I have two bit lines, a blue bit line and a red bit line. Your cell is either connected to the red one or the blue one, depending on what ROM storage you want. The RAM storage is still in the magnetic term junctions. The ROM storage is in the connections, whether it's connected to red or to blue. Now, during RAM operations, the standard operations, I activate both lines. As an example, if I'm reading, I activate both the red lines and the blue lines, and I do my read operations or write operations, just like what I do otherwise. And the RAM data is available. Now, for my ROM operations, what I do is I actually, same word line, I turn it on. But in this particular case, I turn on one of the bit lines. In this particular case, let's say I turn on only the, activate only the red line. And if I do that, then you can see that the ROM storage basically for the leftmost column, when it reads, try to read the ROM, it's going to see infinite resistance. When it reads the middle one, it sees a resistance of resistance of the MTJ, right? Not an infinite resistance, but the resistance of the MTJ. And this one basically ends up seeing again the last one in infinite resistance. So infinite resistance can be 1. The ROM, the MTJ resistance, whether it is R on or R off, doesn't matter, could be 0. And so what you really need to do then is change your peripheral circuitry slightly, the sense amplifier, to be able to do that, and effectively you get ROM without an extra cost, other than some cost for the peripheral circuitry. By the way, the blue line and the red line doesn't cost you in terms of area. What we did is we actually put it in our PUMA simulator, where each of the cores now, really rather than having the map table in the DRAM, is now in my IMC macro. The IMC or the CIM macro, the computing memory macro, not only does matrix vector multiplication, but also has these ROM storage at the same time. And if I do that, it actually is kind of interesting results, because a lot of times when you're doing, for example, LSTMs and all, it is very important to do sigmoid, tanh, and softmax computation. It's also important for transformers. I am not showing the results here of transformers today, but for LSTMs, it actually shows about 49% energy savings by avoiding the DRAM access, and a good amount of speed up, and really coming from the fact that you don't have to go to the DRAMs to fetch these values of exponential functions and so on. Finally, I just wanted to very quickly talk about the fact that computing memory can be done in DRAMs. One can potentially think of As an example, I'm showing a DRAM here. There are data rows in the DRAM. I actually select a few rows, which I'm showing in the bottom, to do which I call compute row. And these compute rows are really, in this particular case, kept for in-memory addition operations. So I can take data from, for example, the top side, the data rows, and put it in the compute rows, turn on some multiple lines, and this is basically activate the multiple lines in the compute row for A, B, and C, so that you can get majority functions with some, there's almost no changes to the architecture. Adding some extra transistors, one can show that one can do majority operations and the C out operations. So effectively, you're taking the data from the data rows, putting in the compute rows, turning on multiple word lines in the compute rows to be able to actually get this majority operations or the carry out operations. And once it's done, you store it back in the sum and the carry sections of this memory array. If you do that, and we actually did a case study on computing DRAM-based k-nearest neighbor acceleration, where the host processor does top k sort, and the main memory does basically the Manhattan distance computation. What we found is that with the x86 2 gigahertz kind of processor architecture with the L1 cache and L2 cache of the size that's shown here on the right, and a main memory size of 124 MB and so on, turns out that I can do an improvement in execution time of about 11.7x performance improvement by doing in-memory computing in the DRAM in this particular case. So that's all I'm going to talk about in the memory side of things. But I thought that since I started with completely vision-based navigation, where we started with sensors, even cameras, hybrid algorithms, and the hardware part of it is not all in memory computing, but we implemented this in a real system. I did not have time to go much into the algorithms of optical flow depth estimation and so on using these hybrid network architectures or even the event-driven cameras. But just wanted to show you that this is a system that was implemented. This is at the bottom showing the DVS camera right here. And the drone is right here. And the basic idea is that it's supposed to track the movement of the ring. And once it tracks the movement of the ring, it then flies through the ring using these hybrid network architectures that we talked about. And again, showing the possibilities, though I must admit that the computing memory is not there in this particular case. So with that, I'm going to end it with some parting thoughts. As simple as the fact that algorithm hardware co-design guided by biological principles can potentially be a pathway for the next generation of neural computing. I wanted to acknowledge whatever I presented today, certainly the work done by my students, and I'd like to acknowledge all their contributions, and finally acknowledgement for our sponsors. Thank you, and I'll try to answer any questions that you might have.
Thank you, Kaushik, for this very nice talk. So to the audience, if you have any question, please do it in the chat channel as soon as possible. I'm seeing no question for the moment. So the approach, Kaushik, the approach you talked about, which ones are already being used by the industry?
A good question. There's a good amount of work that people are looking at in the industries. I mean, there's a good number of startups doing in-memory computing, right? In terms of the network architectures, which I didn't spend much time on, recent work, certainly the standard DNNs people have been implementing, but there's a huge amount of interest now in this new cameras, the DVS cameras, and coupled with that, these hybrid architectures can potentially be quite interesting and useful. It's sort of still, some of these are in nascent stages, but a good amount of work has also started in the industry in each of those topics.
Okay, thank you. I'm seeing no questions yet in the chat channel. Well, there is one by Florian from UK, University of Bath. So, do you see all machine learning migrating towards fully spiking architectures or something hybrid?
Yeah, good question. I don't believe so. I don't believe so. I mean, spiking certainly has its own niche. Spiking does make sense in a kind of applications like sequential applications and for the kind of inputs that I just talked about. I personally believe that when it comes to SNNs, training SNNs is difficult, right? So the hybrid architectures are sort of taking the best of both worlds. So if you think about it, SNN has a membrane potential, which is like a memory. ANN doesn't have that, but there are different ways of taking care of that. So if I can have one layer of SNN and the rest are ANNs, training becomes easy, and you can still capture, for example, the sequential information. So to that effect, I feel that in case of some of these IoTs and other kinds of applications, drones and all, it does make sense to have these hybrid kind of architectures. Are SNNs going to take over everything? Absolutely not. I think in some of these niche applications, I feel that they can be quite exciting and interesting, can potentially give you less number of parameters, and has the potential of giving you better accuracy in some of these cases too, because they capture, you know, um, uh, this timing information, sequential information better, compared to, for example, LSTMs, and with less number of parameters.
Thank you. I see no more questions here in the chat. So I'd like to thank you, Kaushik, for this very nice talk. I
Thank
hope
you.
to see
Thank you,
you in
Ricardo.
person in the near future. And I know there is another one arriving from Saeed Shafayed Chowdhury from
Yeah,
Purdue.
yeah, he's
Taking off implementing hybrid archetypes be a challenge?
certainly. I mean, well, question of course is what is meant by architecture, um, and it turns out that certainly implementing um, a hybrid architecture, the training is going to be certainly a little more time consuming possibly than, for example, a standard DNN implementation. From the hardware point of view, um, uh, again, if I, depending on how much of spiking layers you have, some changes would effectively make those implementations faster and better. For example, if I talked about in-memory computing, but for a spiking domain, if I'm using wiki integrate and fire, turns out that not only I can do in-memory computing for the weights, but also I might have to update my membrane potential. Can I do in-memory computing for updating the membrane potential also at the same time? So that becomes important. And depending on how many spiking layers and how you're doing it, and if you don't have too many spikes, and even computation can be quite useful because the spikes are usually rare.
Okay, thank you very much. So I see no more questions. So thank you, Kaushik, for the very nice talk.
Thank you.
And I just would like to remember the audience that you still have about a little bit less than 1 month to submit our papers for LASCAS, the Sequencing System Society flagship conference. And we are preparing a very nice event for all you that are coming to the south of Brazil at end of February next year. So thank you. Bye bye. Have a nice weekend, and
All right.
see you in the next CASS talk.